Oğuz Hocam, you can, the floor is yours.
Hello, everybody. I hope my sound and screen is okay. Since I'm out of internet for the office for the moment, I'm just connected through my phone. Hopefully this will work out.
It looks good.
Okay.
We can hear you really well.
Let's give it a try. So my purpose, original purpose, to introduce the superconductor materials as a continuation of the yesterday's lecture. So it turns out I have to go start from the basics and introduce superconductor qubits for the quantum computing and so on. So in this limited time, I'll try my best. Try to go and cover the many ideas, many topics actually. Okay, let me go through without wasting so much time. So I'll start from this roadmap. I just borrowed this from IBM webpage. And actually, there is a video on the YouTube. Just this is described in detail and so on. As you see, for example, if you look at the 2022, we are here. IBM already achieved, and the progress is actually quite fast. If you consider the difficulties, the scaling, there's really problems with the scalability of these qubit systems and so on. So by this year, 2022, we are talking about more than 400 qubits on this IBM roadmap. So first, I'll start with just a couple of slides. Now, everybody quite familiar, but there are several undergraduate students as well. So this is going to be a quite refreshment for the experienced one. With a couple of words for the quantum computing. So the idea is actually to go be able to simulate the complex calculation like the large systems, molecular dynamics, nonlinear systems, weather forecasting, and so on. So these are complex problems, and with the classical computers, our resources are quite limited. So the idea came why we do not use the quantum mechanical systems to perform these mathematical computations. So it is not a surprise. One statement from the Richard Feynman, he's always visionary. 1981, he observed that simulating the dynamics of quantum system requires classical resources exponentially in the system side. So he already suggested to use the quantum system to simulate these classical problems. Then maybe one famous breakthrough due to the Peter Shor, 1994, he just proposed an algorithm to find the prime factors, which scales as polynomial rather than exponential, as shown on this graph. So again, what is the major difference? If you compare the classical logic, so we have simply based on the analog devices, we just have the bit 0 or the 1. Then we have the gate operations, not and the exclusive or depending on the single bit and the 2-bit operation. Then based on this, all series of the computation operations can be generated using these things. When you go to the quantum, now we don't have the 0 and 1, but the so-called the qubit, which is represented here. So we have a two-level system, 0 and the 1. Then we have the superposition of this guy as given like this wave function that forms the quantum bit. And so again, similarly, analogous to the classical approach, we have a single qubit. Now we have the unitary transformations. Those are like the rotations and so on, and a 2-qubit operation for the control node. And using these two logic gate, actually, geldi mi? So our internet is back. I think I can connect. If you just give me just 1 second, sorry, I'm just checking. Hello, am I okay?
Yes, we can hear you really well.
So now I'm using the normal internet, so it shouldn't be any problem. Okay. So if we look at the key to the quantum computation, we need a two-level system. So the physical system that we are going to realize has to give this specific well-defined two-level system. Then we can write the superposition for the single qubit. Then interference of the 2 qubits actually lead to the this entangled form. So we will rely on the entanglement. So what is the advantages of this instead of just using 0 and 1? In order to perform parallel computation, you really go the parallel implementation for the classical approach. But here, in this case, actually, with a one shot, since you have an entangled state, you perform all the operations. Then at the end, you just observe, you measure. With the measurement, actually, you collapse the state, you get the final parallel computation, just quite naturally with this entangled state. So here this is just one example with a 300 qubit that can register 2 to the 300. So that's almost I will not try to read 10 to the 90 numbers you can register. Instead of going to parallel implementation, you just directly go to the parallel computation, then you will benefit from the scaling with this. So I will not go to look at each single one. So these are, we have the, as I said, these are the classical logic operations. So there are 7 different type of the logic gates here based on the 0 and 1. Similarly, the corresponding quantum logic are established, and using these gates, actually you can go and use these machines and implement your computation using this. As you realize, the single bit operations, so these are just a superposition, just based on the different type of the rotations and so on. Then you have also 2 qubits operation that complete the whole logic gates necessary to have the computations. I think. And maybe I should say a few words as well. This is the so-called DiVincenzo criteria. So these are the his 5 statements, requirements for the quantum computation, and actually 2 more for the quantum information as well. So these are quite reasonable things. First of all, you should have a scalable physical system of the qubits. So this has to be well defined, okay, well defined, and at the end you should able to scale this guy. So as we already discussed, we have the we need a 2-level system. This can be this is introduced naturally by the quantum mechanics, since the energy levels are quantized energy levels, discrete values. Even if you look at the atomic levels, you start from the ground state, the first excited state. So if you look at the hydrogen, you start from the 1s state and the 2s and so on. So actually, this is an infinite series of the discrete energy levels. What you need a well-defined, well-separated as well 2 energy levels to introduce your physical qubit system. Then once you realize this system, then the second condition is you have to able to initialize, so you have to prepare that particular specific quantum state to start the computation. And this has to be repeatable, okay? So it shouldn't be random. Then that means you need to have a control to initialize your qubit, physical qubit in the same cell, same manner for each time. Then here you might need the quantum error correction as well, and so on. But I'm not going to that discussion here. And the third, we need a universal set of the quantum gates, since you know, at the end of the day, we need this for computation. We need this logic operations. Then we need this case. I already summarized in the previous table for the classical as well as the quantum computers. So with single qubit operations, just based on the rotations, and the 2 qubit for the control knot using the entangled property of the 2 qubit operation there. Then fourth is the for readout, you have to measure, then you should able to measure in the correct way without perturbing the states of the other qubits and so on. So for the quantum measurements, actually we are looking the probability density of these. If you simply for the two states for two levels, I can summarize simply like that. And the last one, this is also critical. Physical systems should exhibit long decoherence times as well. Since I mean, in yesterday talk, I provide a couple of numbers for the lifetimes for the different defect states and so on. Even today, I'll show different type of the implementation. So you have to initialize your system, then your computation, then you have to enough time for the measurement. So during all these times, actually, you need to preserve your state of your qubit. But there is always interaction with the environment, and the environment actually destroyed this entangled system. So that's why the coherence, the lifetime is quite critical. It should be long enough that we have a chance to perform all these operations. Okay, so I borrowed this figure from Google as well. So when we look at the qubit implementation, we have to look at three different aspects. So the coherence I already mentioned. The system should preserve the quantum coherence. We should have the functionality with these two levels. Then we need a scalability as well, since in order to have reasonable, practical quantum computer, you need a number of qubits together. So here, this diagraph just summarizes different ones, different approaches. While someone has a long coherence time, but they are not easy to scale the system and so on. From these different approaches, today I'll go through the ones with the superconductors, superconductor qubits. So they have reasonable scalability, coherence, and functionality.
Okay. There's a question, what do we mean by scaling?
Okay. So, for example, in the first diagram, I showed the IBM machine with a different number of qubits. You don't go, you cannot, so here, for example, it starts like 27 qubits, then in a year it goes 65 and so on. Still, these are small numbers, okay? With the scaling, I mean on that chip, you include that many qubits for your within your processors. So in the classical computers, now it is the nano scale. So we have the so-called Moore empirical law that describes number of the transistors within the processors. Similar to that one here, we need the qubits in order to perform these operations, and you need to increase the number of the qubits in your chip, processor chip. And I'll also make a comment here. So now the level is around this number. So with this, actually, you can represent this many states to the n state. So we need a finite number that not that large as the classical processors, but still we need that many qubits. That's for scaling, increasing the. Yes, this is a little bit mess, but it is the same slide that. So with the, this one, you have this many states. Okay. So now I'll open another section. Then I visit the superconductivity. So you might be quite familiar, but I'll give a very quick review about the superconductivity, starting from the original discovery by Kamerlingh Oğuz. So this is a picture from his lab himself and his technician. There is a quite controversial stories between the Oğuz and the lab technician about this discovery and so on, but that's not our point today. So here, first, let me motivate. So the refrigeration is quite important. People work on that to go lower and lower temperatures and so on. I will not go to the this process there, but if you look at the in physics, we work with the Kelvin, absolute zero. Then we have a liquid helium around 4 Kelvin. Then we have a liquid nitrogen around 80 Kelvin. Then room temperature is around 300 Kelvin, and so on. So in the ambient environment, we live here, but most of the, at least the prototype physics experiment performed over these low temperatures. So why I start this? Okay, so this is one piece of information. Then another piece of information, the general property of the metals. I'll concentrate over the electrical conductivity. If they are a pure, perfect conductors for the electrons. So simply we can describe this starting from the root model, then extend to the Sommerfeld, simply like that. So in metals, what we have a positive background formed by these ions. Then the electrons form a C. So electrons are loosely bound to the atoms, but they can in the metallic structures they easily move around and they form this electron C. And within this potential, these electrons move freely till they hit some scattering center. Okay, this can be like the lattice vibration, the phonon scattering, and so on. These are all these scattering mechanisms will lead to a resistance. So if you apply the field, you will see the current here, but because of this scattering centers from this semi-classical model, we can describe the conductivity in metals and so on. Okay, so let me return back to the superconductivity. So the original question at the beginning of century, what will happen to this resistivity as you go to the low temperatures? Okay, so at that time there were 3 different stories around. So if you go to do this, let me go chronologically from the Matheson. This is the oldest one, this black curve here. It says that the residual resistivity goes to the finite value because of the contamination defects and so on. If you go to the, if you reach the low temperatures, absolute zero. Then on the other hand, two opposite, not opposite, but two different approaches. The Kelvin say that the electrons will freeze, so the resistivity will grow to the infinity, while Dewar says the lattice will be froze, so the electrons will not be scattered at all. Resistivity will go to zero. So this is another question, research question at that time. So here I just summarize. So this is the same picture I showed at the beginning. While they try to reach low temperatures, so at that time, I mean the helium was known, but it has not been liquefied. So their try is just to get the liquefied helium around that time during this experiment, and they were measuring the electrical measurements using the mercury on the system. Okay, so all of I mean, sometimes the accidents happens and so on. They observed a short circuit. And actually, there is a quite nice story describing there is a one issue 100 years at the century of the discovery of the superconducting. There is a special issue on the Physics Today. They describe in detail all these stories and so on. But during these mercury experiments, while they are trying to go liquid helium, actually they got a short circuit. First, they on stall, that's a mistake. They repeat the experiment and so on. So eventually, they got this curve. So horizontal axis is temperature. So the resistivity comes, then all of a sudden it drops to the zero around 4.2 Kelvin. This is the liquid helium temperature. So this is the boiling point is 422 Kelvin. So just try to get this. Actually, they end up with a quite astonishing phenomena. This is the statement directly from Oğuz. Extraordinary electrical properties may be called to superconducting state. So this is the starting of the story. This is a much pure graph from the Kittel. At the transition temperature at the TC, you go to the zero resistance from normal state to the superconductor state. The definition of the superconductivity, we can simply summarize after certain transition, we have this transition to the zero resistivity compared to the ordinary metal shown here. Okay. Time goes by, I'll try to go a little bit fast. So, I mean, this is the original conventional superconductivity, and this is described. So here I'll show a simple animation. So we have the ions, then we have the distortion of this lattice. So they have a periodic, the crystal structure has a periodic position. The ion sits at the periodic position at this zero temperatures, but with the temperature, actually they move around a little bit, that vibrate around a little bit. These are called the phonons. Okay, I have a better animation. I'll come that. So based on this interaction of the electron and the phonon, the theory developed after 40 years from the first observation of the superconductivity by Bardeen, Cooper, and Schrieffer, the so-called BCS theory that explained this conventional superconductivity. And just look at, this is 1957, the first experiment I showed, 1912, it's 40 years after the observation. The idea is simply like this. You have electron pairs interacting via phonons, they form a Cooper pair. they form a bound state called as the Cooper pair. Why this is so important? But this is the same lattice. You see these ions are moving, so you have a distorted positive charge. They attract 2 electrons. These 2 electrons just form a pair and they move by pair. Okay, not the single electron as I tried to show at the beginning. Now they move together as a pair. But this makes the physics quite different because the statistics is completely different. The electron as itself has a spin 1/2 particle, and that obeys the Fermi statistic, and it obeys the Pauli exclusion principle. Okay, so in each state you can, Pauli exclusion principle says that in each state you can not accommodate the particles with the same quantum number. So what does that mean? Since electron has spin 1/2, you can accommodate only 1 up, 1 down electron for each quantum state. Okay, then it obeys the Fermi-Dirac distribution and so on. But what happens when you form the Cooper pairs? So 2 electrons come together with the phonons. Now they have the spin 1 particle, so they are bosons. Okay, and the bosons have the completely different statistic. You can accommodate all these bosons at the same level, since the Pauli exclusion principle does not apply here, and that's the quite critical difference. Okay, maybe I can cut the long story short. So because of this, actually, this Cooper pair avoid the scattering through the lattice and so on. So avoiding this scattering mechanisms, actually, you go to the zero resistivity. Well, this is the result of the BCS theory. Later on, we have a different type of the superconductors discovered, like the high TC materials. So these are based on the ceramic materials. They have a different, they don't obey BCS theory. It's more complicated structures, but these basic principles still we have this sorry. We have the zero resistance. Let me, without going to this magnetic field and so on, let me stop that. Then maybe I'll mention one more thing here. So in the normal state, for example, even at zero temperature, we have the Fermi-Dirac distribution. So here, till the Fermi energy, all the states are occupied. Okay. With the formation of the Cooper pair, actually there is a opening of the band gap, superconductor band gap, because of this bound state. So we will see the implication of this in a minute. That's why I'm just mentioning this without driving that. Then there's another thing I have to mention is the flux quantization. So this is an experimental observation at 1961. This is just after a couple of years later from the BCS theory. Now here, if you look at here, this is a superconductor ring, and if you apply that magnetic field, the superconductor state excludes the magnetic field. So if you look at the magnetic flux passing through this ring, so if you look at this data, you see that this plateaus. So actually there is a quantization of this flux in terms of this unit. HC over 2E. 2 is the charge unit for the Cooper pair. This is one way also referring that apart from the gap experiment. In a simple approach, we can explain this flux quantization, but I'm quite late. I'm just skipping these parts, but I'll mention one more thing. We need one more piece of information here. That's the Josephson effect. So he's a bright physicist. Actually, he discovered this effect in 1963 as a very young PhD student and end up with a Nobel Prize, 1973. By the way, discovery of the superconductivity got the Nobel Prize on the BCS theory got the Nobel Prize. So these are all Nobel Prize studies within the development of the superconductivity. So here in the Josephson effect, what we have a junction. So you have a two superconductor material separated by an insulator in between. Okay. So the insulator, just simply remember, in the metals we have the free electrons moving around. In the insulator, we have a band gap between the valence band and the conduction band, and that band gap is large, so we don't have any conductivity at all. Okay, so in that sense, this structure, two superconductors are separated by this material, insulator material. So very quickly, I'll show the simple tunneling experiment. So if you have two normal metals, so on the left side and right side separated by some barrier in between, this is a thin insulator. So this is another quantum mechanical phenomena, the tunneling phenomena. So if you under zero bias, the Fermi levels are aligned, you have nothing, zero current. But when you apply the bias, then these occupied states from one side can tunnel this barrier region to the other side, to the empty states. And if you look at the current, that is this red curve here. So with as a function of the applied bias, you can measure the tunneling current. So they can penetrate, the electrons can penetrate through this insulator, through this barrier, and you can have this tunneling. So this is one important thing, and this is realized like the scanning tunneling microscopy and so on. But let's go with the Josephson. So here, what I'm showing, the same simple energy analysis, that we have one normal method, then the superconductor on the second side. Okay. Then here, one difference, you see the gap, open gap in the superconductor material by the Cooper pair, as I just mentioned. Then again, if you apply the bias as a function of the bias, then what you see first, this Fermi level just within the band gap region, okay, and so there will be no tunneling current, while since there is no corresponding state on the other side, till when this Fermi level hit the edge of the this band, this upper band there. Okay, and actually this is nicely observed on this tunneling experiment. You see, first there is no tunneling current, so you have to overcome this band gap. Then you have the tunneling current and so on. Then you can do the same thing. So this is the dash line is the finite temperature effect, this smoothing comes from the temperature. Then you can repeat the same thing with the two superconductors, as I showed. Then you will have a tunneling curve like this. So, okay, we have a supercurrent. If you have a two superconductors separated by a thin insulator in between them. And okay. Then, so based on this, we can very quickly, sorry, time fly by. Very quickly, let me review the Josephson effect as well, based on this tunneling. So we can have the DC or the AC, then macroscopic long-range quantum interference. Since this is going to be important for these device applications, very quickly, let me go through the DC Josephson effect first. So we have two semiconductors separated by an insulator there. Okay, there is no bias in this case, in the DC case, between them. So with a very simple approach, we can describe this like this. So psi1 and psi2 are describing the first superconductor and the second superconductor. There simply we can write that in terms of the phase and the particle density in this simple form. So this tunneling effect is simply described by this. So this is the change, the rate of the from the first region. T is the tunneling operator, or the transfer frequency, you can say, to the second part. Then that becomes the psi2. Then we can write the symmetric one from 1 to 2 or 2 to 1, vice versa. So if we use this ansatz, and if we implement this into these equations very quickly, I'm not trying to go one by one. You can collect the terms, just inserting for both regions. Then on the right-hand side, we end up, if you rearrange, you end up a simple form based on this phase difference. Delta is the phase difference between these two guys. Then just looking at the real parts and the imaginary parts, okay, from the real parts and the imaginary parts, we can get the information about the number density and the phase change. So simply, I mean, if you look at this, is the M1 is the number density in the first part. So this is the change of that. So that's simply, if we count that, then we can write the current just in terms of that. And actually M1 and M2 should be opposite to each other, this change, since it's going along the one direction. So we can combine with a minus sign. So based on this simple analysis, just looking at this rate, then we can conclude there will be a current, a super current, this tunneling current based on this DC Josephson effect, based on the sign delta. Delta is just the phase difference between these two guys.
Hocam, we have 5 minutes.
5 minutes, sorry. Then, okay, we can have the same analysis, exactly same thing, same type of the calculation, if we add a bias as well. So this EV terms as included, the bias. Then when you have the bias and carry out the similar simple analysis, then you get a oscillating current. You see here now we have a time-dependent term coming from this bias term there. that will give this oscillating Josephson current. And if you have a loop, as I already showed the flux quantization, we can have this quantized flux and this phase. If you go from the upper and lower end, you can write that difference and the flux change on this slope of the discrete structure. So I spent on this since these are all used on this superconductor qubit. As I already said, there are many different approaches, but the one reliable one is the superconductor one. Because of the several advantages. Maybe let me give at least the basic idea here. So we are looking at the quantum. We need two-level system, two-level quantum system. Okay. So the original idea is simply like this. Just assume a circuit. You have like a inductor and a capacitor. Okay. So this LC oscillator circuit, we study even on this simple general physics courses like that. If you look at the quantum version, it behaves like a quantum harmonic oscillator. Okay. So I'm just skipping the algebra here. So on this one, it behaves like a quantum harmonic oscillator. That means we have energy levels, uniform energy levels by this. So, okay, we have levels, but this is not that useful for qubit operation since, for example, if you try to pump this system with this energy of photon, actually, since this is uniform, you cannot differentiate the two level. So it can jump for any levels and so on. So there should be some non-uniformity here. This is one idea. And actually, okay, so this actually shows. So if you start from the LC, this can be exactly like this is the harmonic oscillator. But instead of inductor, now let's introduce the Josephson junction here. Okay, so with the Josephson junction, now we end up an anharmonic oscillator. Okay, then with this now the levels separations are different. Then actually we can isolate ground state and the excited state, and we can use this for the two-level system, two-level quantum system. So that's the idea. So based on this Josephson junction, several versions are introduced. So the basics ones are the charge qubits. So in the charge qubit, we have the Josephson junction and the Cooper-Wales tunnel through the other ones. We have the phase qubits. So these are the names are just describing the people behind them. Based on this phase difference, as I showed, I pass a little bit fast, but on the AC Josephson effect, you see the phase manipulation. Then also it can rely on the flux as well. I'm just quickly trying to summarize. Okay, so in the charge qubit, we have a bias. Then there is a gate capacitance here. So with this gate capacitance, actually you adjust the charge state of this Josephson junction there, and you end up an energy spectrum. So as a function of this capacitance, then you play with this charging of the system. And the Hamiltonian, it can be shown that can be written like this, and we have a spectrum there. Then these first two levels, just adjusting the value of this, adjusting to this separation and that separation, these two levels can be isolated, and these two are just used for the this. Then for the flux, now we have this squid structure. In that case, we have a double well potential with this type of the Hamiltonian, and this it gives the two levels there. Then for the phase,
we're out of time, but could you?
Yes, I'm just showing this, and I'm stopping. Then it gives this type of the profile and these things, and it operates through those. Okay, I'll stop there. So anyway, at least I introduce the basic idea behind this case. So sorry for taking over time. So I'm stopping here. Thank you.
Thank you, John, for the very nice lecture. There's actually one question in the chat from Şevval Taşdemir. Actually, Cooper pair act like a new particle, contains two electrons, have half spin. Can we say that? So
that they are not separating. It forms a bound state. The Cooper pair forms a bound state. So it is a spin bound system. And because of that bound state, we have the gap opening and so on. So separately, they have the half spin, but they form the pair as a bound state. So maybe you can think, for example, hydrogen atom, then you get another hydrogen together, you get the hydrogen molecule. Okay, hydrogen molecule moves together and so on. Here, Cooper pair also form the pair, and they move together. They are not independent from each other. They move together. It's a spin-bound system. So that's why it obeys the boson statistics.
Okay, there are many. Maybe there are more questions. One thing that waiting for questions is that the place that Kamerling Honors found superconductivity is still there, the building, but now it is law faculty, still part of University of Leiden. But you can still go visit if you want. It's not so far from where I am now. So, okay,
there's a controversial story, you know, and these are all taught on this physics today special issue.
Right, exactly. Özgür Hocam.
Thank you, Necam. I have a question, maybe also to all the experts here on condensed matter physics. Maybe you have some insider information. So last year I was very happy because now the trend in quantum computation is that it is somewhat in the monopoly of big companies because all these quantum materials are very expensive and require low temperatures. But last year, Oğuz Hocam also gave a talk about it. There is a very high temperature, even close to near room temperature superconductors. And I was hoping that this could maybe eventually make quantum technologies more public. And but then I was a little bit disappointed. There is now a lot of controversy, papers are withdrawn, things are very hot. So what is your opinion about them?
Okay, so actually in my original plan to include those room temperature superconductor materials on today's presentation, but then I realized I have to go visit the Josephson effect and so on. I took those parts out. So these materials, okay, there is an objection, but there is an experimental fact. I believe still, okay, let me first maybe not everybody familiar with the structure and so on. So I think 2-3 years ago, the people from geophysics lab Nowadays, nobody is there. Assembly moves to Chicago, Emirates in Germany, and so on. So independent from each other, two different experiments, what they do under high pressure. So they have a, within the diamond anvil cell, so between two pieces of the diamond, they make the synthesis over there as well, then apply the high pressure to this material. This material is the hydrogen-rich material, like lanthanum H10, and so on. There are so many hydrogen there. Then when you compress, they got the superconductor transition at the very high temperatures. I think in the first experiment, it's like 215 Kelvin and so on, even, but later this approach to the 300 Kelvin, but the pressures are really high, 200, 250 gigapascal, and so on. It's quite exciting. A lot of people try to do this and do the theory as well. I mean, the idea is not that surprising to me, since we are familiar a little bit with the metallic hydrogen. The metallic hydrogen has been a quite interesting research topic, maybe last 30, 40 years. Even the first prediction from the Mermin, if I remember correctly, if I'm not mistaken, and so on. So on this, these are really hydrogen-rich systems. So when you compress, actually, you get the packed hydrogen system. The other part is, I think, the metal, the lanthanum, and so on, is just making the host. Still, it's not a fully resolved thing, and so on. People try to get the low pressures, even ambient pressure, to preserve the that structure and the things. But there are a couple of objections from theoretical things, not from the experimental side. As far as I know, several experiments repeat that. Then we did some calculation using the machine learning techniques, and we predict some other material with other metals. We haven't published this yet. We predict from machine learning, then just using the standard DFT calculation, we try to get the transition temperature, try to confirm that, and so on. But I think, yes, you are right. This might be a quite important opportunity, but still we need some years to establish things, at least to go to the... Now, you see, what is the cost? You raise the transition temperature, but you need the high pressure. That's the...
But these theoretical papers also argue if you just increase the hydrogen deposition, then there is still some opportunity that you can reduce the pressure requirements, less severe regimes. Yes. So
yes, that's
very
the idea.
I am happy that you think this is a real science and it is going somewhere. Yeah.
Yes.
Good.
So I mean, for example, lanthanum 10 gives the transition, but that's a strange. I think lanthanum H20, let's say like that. I don't remember the exact number. Some higher number don't give, and so on. There is some strange things like that as well. But with some other metals, maybe some other structures, it's possible to go lower pressures. That's the issue there.
Great. So I will be able to discuss this more technically with you guys. I also like this direction. Okay. Thank you so much.
Let's do that later on. So let's just, I think we're way out of our time. I think we can announce the session is finished.